Dr. Nathaniel Frissell is, by the way, Whiskey 2 November Alpha Foxtrot, is going to give a talk on the HamSCI, Personal Space Weather Station Architecture, Early Observations, and Applications of Radio Astronomy. He's a professor of physics and engineering at the University of Scranton and the leader founder of the Ham Radio Science Citizen Investigation, HamSCI community. Nathaniel specialized in ionospheric impacts of space weather and completed his PhD at Virginia Tech with the Super Darn Group in 2016 and led the Solar Eclipse QSO party in 2017. Okay, Nathaniel, go ahead.
Thank you very much, Rich, and thank you to everyone for letting me present today. Yes, so we'll be talking about the HamSCI Personal Space Weather Station, the architecture, and applications to radio astronomy. And I'd like to thank everyone on my co-author list here. As you can see, it's a rather extensive list. But one of the reasons for that is the way we operate at HamSCI. We're developing this personal space weather station, and we're having many different people contribute to different parts of it. So you'll see their names throughout the list. Some of the first names you see here: Scotty Cowling, Tom McDermott, John Ackerman. They are some of the lead design engineers for the TangerineSDR that I'll be talking about today. So I have them up front here. And then Dave Typinski from the Radio Jove community really helped me out with coming up with some applications to radio astronomy and giving some example spectrograms that we hope to be able to use the TangerineSDR for. So as an introduction, the HamSCI Personal Space Weather Station, this is a National Science Foundation primarily funded project with also funding from the Amateur Radio Digital Communications, ARDC group, to develop a ground-based system for observing space weather that can be used by amateurs and professionals alike. And so it's really designed for the amateur and space science ionospheric communities. I came into space science being a ham radio operator first. I started as a high school student in ham radio, and that really is what led me to this career in space science and atmospheric physics. And so that's where this motivation comes from. And at its core, this project is going to have a very flexible precision software-defined radio instrument known as the TangerineSDR, which I'll be spending a lot of time talking about today. And this TangerineSDR will meet key requirements needed for scientific use that are not found in your typical communications grade SDRs. And therefore, this will hopefully be of interest to the radio astronomy community, in addition to the amateur radio and space science community. So I've divided my talk into 5 major sections. So I wanted to give a little bit of introduction to amateur radio, radio propagation, and space science. Then I'll talk about the Personal Space Weather Station project as a whole, because there's a lot of different components to it. Then I'll focus just on the TangerineSDR, and then I'll show how the TangerineSDR, how it might be used for Radio Jove, and then considerations for radio astronomy in general. So many of you here probably don't need this slide, but in case we do have some people who aren't radio amateurs, what is amateur ham radio? It's a hobby for radio enthusiasts, people who are communicators, builders, and experimenters. And we in the amateur radio community, we come from all ages and all walks of life. In the US, there's over 760,000 amateurs and about 3 million of us worldwide. And we all are required to have a license. And to get that license, you have basic RF electrical engineering knowledge. And it really demonstrates that you have a personal interest, a vested interest in what you're doing. And so this really makes this group ideal for community citizen science. And every amateur radio station has a government issued call sign, which, as Rich said, mine's W2NAF. So you'll see these call signs spread throughout the presentation next to people's names. And so, as I said, I started my interest in ionospheric science came from being an amateur radio operator. But then as I did my PhD at Virginia Tech, I joined the professional science community. And I saw a need to really join these two communities together in a way that's, perhaps more formal than was done before. And so I was able to start the Ham Radio Sciences Investigation. or HamSCI. You could go to hamsci.org for more information. But our main objective is to advance and encourage advanced scientific research understanding through amateur radio activities. We want to encourage the development of new technologies to support this research, which is exactly what the Personal Space Weather Station project is doing. We want to provide educational opportunities for the amateur radio community and the general public. You know, I often give talks to radio clubs and to scouting groups and things like that. And then we also have our annual HamSCI workshop, which is how I met Rich Frissell. So why is there such a connection between amateur radio and space science, ionospheric science? Well, that's especially because of skywave or skip ionospheric propagation. Amateur radio operators like to communicate around the world using especially the high frequency bands between 3 to 30 megahertz. And these are able to travel around the world because they are refracted by the ionosphere. In this ray trace, these colors are showing plasma frequency or electron density. And then these rays represent signals at 14.03 megahertz going between Florida and Wisconsin. And you can see that there's a refraction that causes these rays to bend based on how much electron density, what the electron density gradient and density profiles are in the ionosphere. So this was a simulation during the 2017 eclipse. You can see when there's a red line there, we have communications. When there's between the two stations, when there's no line, there's no communications. And this is really critical here because as the radio wave propagates through the ionosphere modulates the signal, and you can detect those modulations over here and hence remote sense the ionosphere and the coupled geospace system, which is attached to it. And similarly, this is another form of the ray trace. So here, instead of changing the background electron densities, we're keeping that the same. This is using the IRI model, but we're changing the radio frequency. So you can see here's a 15 megahertz frequency. As you go lower in frequency, you get more refraction. Here's 10 megahertz. So for the from WWV in Colorado to my station in Pennsylvania, you get one hop at 15 megahertz for this particular time of day, and 2 hops at 10 megahertz. So you can see there's a this refraction has there's a frequency dependence on the amount of refraction you get. So what's really neat is there are now these systems that have been in operation for now a whole solar cycle that are constantly monitoring amateur radio communications. The reverse beacon network, which monitors CW Morse code traffic, WhisperNet, which is a weak signal propagation network. It's a digital mode, and PSK reporter, which is monitoring, say, FT8, PSK31, other digital modes. And all of these networks are, quasi global in coverage, and they're logging all of their communications, all the communications that are happening. So you can go back and you can study the propagation effects and the space weather effects on the communications. And so here's some examples of that, of what we can do with amateur radio research. So during the 2017 Great American Eclipse, I organized with other people in HamSCI the 2017 Solar Eclipse QSO party. And so we had amateurs, it was a ham radio contest that took place before, during, and after the eclipse. And we were able to see the eclipse effects in the radio communication. So in this example, we're looking at the 14 megahertz 20 meter band. At the middle of the graph here is when there was maximum eclipse. And then this is an hour and a half before the eclipse, hour and a half after. So you can see before the eclipse started, there were lots of communications across the United States on 14 megahertz. As the eclipse shadow came across, we saw a decrease in communications as the critical frequency of the ionosphere dropped below this, or the maximum usable frequency dropped below 14 megahertz. The signals escaped into space. The amount of communications dropped. And then you can see that it returned afterward. Down here, we were able to actually model it using that SAME-3 model provided by Naval Research Laboratory. In addition to that ray tracing I just showed you, we were able to get the model to agree very well with the observations. So this was all done with reverse beacon network data. Over here, this is not reverse beacon network data. This is a technique where we're monitoring the Doppler shift of the WWV standard station in Colorado. And here you can see, this was received in Milwaukee. You can see positive Doppler shifts at 10 megahertz as you get dawn, and then negative Doppler shifts as the eclipse shadow comes on and the path length gets longer. And then as the sun comes back, the path length gets shorter, positive Doppler shifts again, and then you get the dusk effects over here. And so you can see this really nice eclipse signature over here. And then right in the middle, you see this little turn that's correlated with a C-class solar flare. So really neat stuff. Here's some more examples of amateur radio signatures. This is looking at both reverse beacon network and WhisperNet over Europe. And you can see this is during a day in September of 2017 where there were a number of 2 solar flares. We're looking at the 7, 14, 21, 28 megahertz band over a period of 12 hours. And you can see that when you get that solar flare, you just get a dropout of communications as observed, that radio blackout phenomena that's been well documented. And what's neat too is if you take the same data set and you just bin it a little bit differently, you can actually see these traveling ionospheric disturbances move as a skip distance moves in and out. And this will correspond with this corresponds with a large scale traveling ionospheric disturbance that can be seen in GPS total electron content data. So here's the peak of the wave, there's a trough of the wave, there's another peak. This moves equatorward with time. That corresponds with this in and out motion of the skip focusing distance. So it's really neat what you can do with systems that already exist. But the thing is, RBN, WhisperNet, PSK Reporter, they're wonderful and we continue to use them. However, they really weren't designed necessarily for scientific use from the beginning. And that's one of the reasons why we came up with this personal space weather station. And this actually came across, this idea first came from Ward Silver, N0AX suggested it. And then I pitched it at the Tapper Digital Communications conference one year, and then again at the HamSCI workshop. And it came together, we were able to form the team to write the NSF proposal, and we got it funded. And so we are working on developing the prototypes of this now. So this is currently in development. And so what is this? This is a multi-instrument ground-based device designed to observe space weather effects both as a single point measurement and as part of a larger distributed network. It's personal because we want to make it small enough that amateurs can use it and buy one, put it in your own backyard and measure space weather effects there. But we also want to make it robust enough that professionals might want to use this as well. So we've really especially for the TangerineSDR design, we've really taken into account what the needs of a scientific user are. And so it's a modular design. So at its core is a software-defined radio. This is the TangerineSDR that I'll be talking about more in a minute. And basically its job is to get raw spectrum, and then you can derive all sorts of different data products from that raw spectrum. We have a GNS or GPS disciplined oscillator and total electron content receiver. This is necessary for doing the precision timing and time stamping. We have a ground magnetometer to sense changes in ionospheric currents overhead and out in space. There's a local computer, which could be something as small as a Raspberry Pi, or you could put something as robust in as a large full-sized computer. And then and of course you can attach, other instruments as needed. So one person in our group is developing a VLF receiver that would go over here. So that's actually in development. All this would go out to the internet. It'll be sent to a public database in central control where the data will be accessible. So that's the general block diagram for the whole system. So what's its purpose? We're really aiming to support two primary groups of users, as I've said. Space science researchers, they want to observe, characterize, and understand ionospheric variability on small temporal and spatial scales. They want to understand the coupling between the neutral atmosphere, the ionosphere, and the magnetosphere. They want to validate and improve models with the goals of prediction and understanding. So they're really looking to understand the environment from a scientific perspective. And of course, we said the other group is amateur radio operators. They want to understand and predict radio propagation to support amateur radio communications, including public emergency service operations, contesting DX long distance communications. And amateurs also want to study space weather and propagation for personal edification and to contribute back to science and the radio art. And as we'll show later, Dave Typinski and the Radio Jove group, when they saw this, they came up to me and said, I think we can really use this for radio astronomy as well. And so that's where the later part of this talk comes in. So where are these going to be deployed? As I said, this is currently a project to develop prototypes rather than deploy a whole network. So at the moment, we're keeping it rather small. People who are stepping up to help out with the development, they're going to see the first modules, but we will eventually be making these available through the Tapper store. And so people who would like to buy them, you'll be able to buy one and use it either as part of the personal space weather station network or for another use that you see fit. So we'll probably see them deployed mostly in North America and Europe initially, because that's where most of the amateur radio operators are. But we do have amateurs in high latitudes and other locations who've expressed interest in the project. And, we could potentially fill out other areas with the help of NSF funding to do deployment in other areas as needed. And we actually have two different versions of the personal space weather station, low-cost version and a performance-based TangerineSDR version, which I'll talk about a little bit more too. So broadly, we are trying to go after these science goals, things like solar flare impacts, which I just showed you, geomagnetic ionospheric storms, internal ionospheric electrodynamics, short time scale, small spatial scale, ionospheric variability, connection to the lower atmosphere. Again, we're trying to make a very flexible instrument so that really its use could be anything that has to do with radio science. It could potentially be applied to based on the interests of the investigator. Here is how our team is laid out. So I am the lead investigator, principal investigator for the whole project, and I'm based at the University of Scranton. And we have my postdoc, Deb Joshi, is there with me, and Veronica Romanek, she's an undergraduate. She'll be giving the presentation after me, talking about the work she's doing. Kung Nugent is another undergraduate working on software for this. So our job is to do radio science and put all of this together. University of Alabama, Bill Engelke, AB4EJ. He and his team are handling all of the software for the central databases, the central control software, the local control software. Tapper and Zephyr Engineering. This is where a lot of Tapper's volunteer, of course. Zephyr is actually contracted. This is where a lot of the heavy lifting is getting done in terms of the actual board development and design for the TangerineSDR and the magnetometer. And these are the names I've shown before. And so their real responsibility is actually designing and building the TangerineSDR and the ground magnetometer. Case Western Reserve University is developing a low-cost version of the personal space weather station, which specifically looks at Doppler shifts from signals from stations such as WWV and CHU in Canada. And NJIT is has oversight of the ground magnetometer science. And Phil Erickson, W1PJE at MIT Haystack Observatory, he's a science collaborator. And then, of course, we continually, from the HamSCI community and even from Tapper, we accrue more volunteers from the amateur radio community and other people as they wish. So here are the two different versions of the personal space weather station. We do have a low-cost version, which we are calling the Grape. You may wonder where all of these fruit names came from. Well, it started with a tapper. Scotty Cowling said, well, there are Raspberry Pis out there, and there are red pitayas, and there are kiwi SDRs, and there are all these fruit names. So he said, we have to have a fruit name too. So he came up with Tangerine, and then eventually Case Western decided on grape for their low-cost personal space weather station. And so the main objective of this is HF Doppler shift monitoring, listening to signals from, say, WWV in Fort Collins, Colorado, and then as the path length increases or decreases, that shows up as Doppler shifts, and here's the eclipse observation I showed you before. The goal for this is about $300, including everything. The Tangerine SDR is the much more powerful HF FPGA based software defined radio. This is one that's potentially useful for radio astronomy as well. And this has precision timing and frequency measurement built in. 2 to 4 coherent phase locked receive channels, cost about $500 to $1,000 US, and it's developed by Tapper. And then over here, this is an example. I guess it's not playing, but right, this we're using an Edis UFE N200 as a stand-in for the Tangerine SDR to make measurements while we're waiting for this to actually be developed. But it'll be similar sorts of things. These are measurements, oblique ionogram measurements made at my house listening to an oblique ionosonde in Chesapeake, Virginia. So a little bit more on the ground magnetometer. This is developed by Tapper and NJIT. And so this is our target performance level for this is about 10 nanotesla field resolution. This is orders of magnitude better resolution than the magnetometer in your cell phone. And we want to do this at a 1 second sample rate. And so this sensor costs about $25. When you buy the whole board and put everything together, you're probably talking $100 to $200 if you include all of the wire and the enclosures to put this into the ground to temperature stabilize it. But this is a prototype board that is developed, and a number of these prototypes have been made and deployed already. And so here's an example. Julius Matty, K2KGJ, has been doing a lot of work on this, and he has a number of these installed at his house in Hillsdale, New York. And so these are the north-south component, east-west component, and vertical down component of the magnetometer. The dark blue is the low-cost version he has running at his house, and the light blue ones are the magnetometer from Fredericksburg, Virginia, available. This data is available on intermagnet.org, so you can see very good correspondence between those. So that's looking good. And so here's a low-cost personal space weather station. The idea here is this board only costs about $30. This is a low IF receiver board where you take in a signal from a GPS discipline oscillator. We're using the Leo Bodner one right now, and you set it to, say, a 1 kilohertz below the signal of interest. So 9.999 megahertz. If you want to listen to 10 megahertz WWV, you put an HF antenna in here, and then you get out the 1 kilohertz tone, and you can get the Doppler shifts. And Veronica will be talking about that in the next talk. What's neat is you can actually build one of these today. If you go to hamsci.org/grape1, we have a plans to build this. You can buy the board off OSH Park. And so we actually have a number of people building them and running them right now. We're also developing a version 2, which will be capable of monitoring 4 HF channels instead of just one simultaneously, and it will have the GPSDO integrated rather than buying one separately. And so here's an example of measurements that Veronica took at her house in New Jersey. And so this is listening to 10 megahertz WWV. Here are these traveling atmospheric disturbances again, and she'll talk more about that in the next talk. So one of the questions is, we've had traditional analog radios, but now we're saying we want to move to software-defined radios for the Tangerine SDR. So why a software-defined radio? So this is, this is a radio that performs a significant portion of its signal processing tasks and software. And this allows for tremendous flexibility in how the signals are processed and enables radio characteristics and purpose to be changed via software. So by contrast, traditional analog radios use purpose-built circuits for specific applications. And one other problem with that is analog systems are often narrowband and hence limited in the amount of spectrum they can collect. SDRs are often wideband. I'm sure probably all of the people on this call are very familiar with software-defined radios by now, and maybe have one or more multiple of the ones you see here. So here's your very inexpensive $40 RTL SDR dongle. Here's a nicer Kiwi SDR. This is the one running at my house, so you can go listen to radio. This is looking at 30 megahertz of bandwidth simultaneously. So these are extremely powerful instruments. But the question is, while these SDRs are heavily defined by their software, the hardware design is still extremely limited, or is still extremely important, and it ultimately limits what the SDR can be used for. And so there are many excellent commercial SDRs on the market like these, but they don't all meet the needs of the scientific user. So for instance, the RTL SDR, it's very inexpensive. It's only an 8-bit A to D in there. Doesn't have a very stable oscillator, doesn't have any precision time stamping. The Kiwi SDR is significantly better, but still doesn't necessarily have the precision time stamping and frequency stability characteristics that you really want in a scientific application. And if you want something that does, you're starting to look at, say, like the Edis's, and like the Edis N200 I have costs $3,000 altogether. So when you need those, when you need the things for science use, you tend to have to pay for it. So what are those requirements for scientific applications? That you need a highly stable clock, you want precision time stamping, phase locked measurements for multiple antennas, facility for processing and transporting wideband data. You want to be able to measure the signal and noise calibrated amplitude. You also want it to be open software and hardware architecture, so you can really get at the data yourself. Because if you're doing radio astronomy, you might have a different application than what we're doing in space physics. So you may want to process your raw samples differently. So being able to customize what you're doing is very important. So we are aiming to bring the costs down in a number of ways. One is we're using volunteers from the Tapper group, which Tapper has a long history, at least 40 years of developing, first the TNC1 and 2, and then they've developed the Hermes software-defined radio before, and now we went back to them and said, okay, can we create a new software-defined radio that meets these needs at a low cost? So we're using some volunteer efforts. We're also able to use the federal research funding to pay for NRE costs, non-recoverable engineering costs for these things, and then we're going to make all of the plans open source. So we're doing that to keep the cost down. And so this includes to accommodate many different use cases. We're really taking this modular approach where we have a data engine that's like the motherboard for the whole thing. We have a clock module where this handles your precision timing. We have a radio frequency module, which can be, you can have different modules depending on if you just need receive applications, if you need transmit and receive, if you need different frequencies. So in clock module, depending if you need very high level performance or just moderate performance and precision, you can switch these out. So modular approach, the current designs are tailored to the personal space weather station application. So our design choices for the initial version of this were made with the personal space weather station application in mind. So this is the overall block diagram for the TangerineSDR. So again, the main focus of our work is the data engine. That's one module. Then we have the RF modules here and the clock module. And I'll talk more about this block in a minute. To make all this work, you also need a computer. we've decided not to include a computer on the board directly because they change so rapidly. So we have just an external port to connect to. A single board computer could be a Raspberry Pi or something more powerful. These are the technical details for each of the different modules. So the data engine, it's going to have an Intel Max 10 FPGA with half a gigabyte of RAM. Let's see, and it will be able to work across a wide range of voltage inputs. It will have a 3-port gigabit Ethernet switch. It's going to have temperature sensors, power on monitor, reset fan header. And then the RF module is going to be a 14-bit A to D. There will be two 14-bit A to Ds on there, and they're going to be clocked together so you can get phase synchronous inputs. You'll have a remotely software selectable attenuation on board. There will be a 20 dB low noise amplifier on board, a fixed 55 megahertz low pass filter, but you can also put in your own optional filter if you would desire. We'll have a built-in onboard 50 ohm noise calibration source, onboard power supplies, and dual SMA antenna connectors. So you can actually, if you're doing, you know, right and left hand, if you're trying to get circular polarization information, you can do that directly with a single RF module. The clock module, our goal is precision timestamping plus or minus 15 nanosecond accuracy and frequency reference parts in 10 to the 13th over 24 hours. And we're still waiting on the availability of the FPGA chips, which I'll talk a little bit more about later. So here's a more detailed block diagram of the data engine. So ability to put on 2 RF modules, so you can have up to 4 inputs. There will be a micro SD card slot. Here's the FPGA clock module. This is the low bandwidth expansion module. It will be compatible with the Raspberry Pi header. You'll be able to attach the ground magnetometer to this. Also, the VLF board will be able to go on this as well. Here's the clock module diagram. So we have a ZF9P GPS module that it will be using. So here's your GPS antenna. This will is a dual frequency GPS module. So in addition to timing information, you can get total electron content. We're going to use a TCXO temperature compensated crystal oscillator for holdover capabilities. And all of this will go into a synthesizer, which will be able to provide up to 10 clock outputs that can then be fed to the data engine. Here's the RF module block. So here's your 2 SMA inputs, your 50 ohm noise source that's switchable, electronically switchable. Here's your electronically switchable attenuation, optional filters. You can see there are 2 parallel paths here, one for each A to D. Here's your low pass filter. There's the there's a low noise amplifier, and here's your 14-bit dual A to Ds. And this all goes out to the data engine. So this is what we're planning on building. And as I said, I went to Dave Typinski who operates a RadioJove Spectrograph. And I said, what are some things you might like to use this for? And so he gave me some examples. So these examples would support the RadioJove project, which again, many of you are undoubtedly familiar with. And so this was a NASA-supported citizen science project started in 1998 to study radio emissions from Jupiter and the sun. And the standard RadioJove receiver, this is a very old version of it, receives a single narrowband signal at 20.1 megahertz. But advanced users often wish to observe wideband spectra to gain significantly greater physical insight into the physical processes. And so what Dave has done with Richard Flagg and Jim Skies, they've developed something called the dual polarization spectrograph, or DPS. And so there's a picture of Dave's DPS over here and his antennas over here. And so this is a system that sweeps 330 kilohertz bandwidth channels from 32 megahertz down to 16 megahertz at a rate of 6.7 sweeps per second as a 12-bit A to D, 50 decibel dynamic range, and 7 dB noise figure. And for his antennas, he's using a terminated folded dipole array, which they have a dual square 8-element array. It's steerable, has separate outputs for right-hand circular polarization, left-hand circular polarization, wideband, decent gain, low cost. And so here's an example of an HF spectrogram that goes from 16 to 32 megahertz made with his station. And this particular example is chosen because you can see signatures from many different types of HF signatures on this one ionogram. So here's some example of some Jupiter emissions over here. It's hard to see, but there's some galactic humps as his station goes through the galactic center. These are propagation TPs, which are believed to be caused by lightning. Sheng Feng wrote a paper about that a year or so ago. So you can see those throughout here. Here's the X-ray radio blackout, similar to what I showed earlier in the amateur radio data. Solar type 3 radio burst emission over here. And then all of these long signals that are narrow band but long in time, those are different radio stations and radio service bands from around the world. But Radio Jove is focused on Jovian Decametric emissions, and these are plasma processes within Jupiter's magnetosphere that naturally produce radio emission frequencies between 3 and 40 megahertz. And so these are known as the Jovian Decametric emission, or Jovian DAM, because it comes from Jupiter and has wavelengths of tens of meters long. And so Jovian DAM above 10 to 15 megahertz can penetrate the Earth's atmosphere and is therefore observable from the ground. And it's also very conveniently within the range of the current Tangerine SDR RF module design. So one type of Jovian DAM is a Jovian L, or long bursts, and this is a Gaussian noise with intensity periodicity of 2 to 10 seconds and a relatively poorly defined spectral structure. In a minute, I'll show you a figure of this. You have as longer, more vertical lanes. It's a combination of the natural variation of the emission source and scintillation due to propagation through the terrestrial atmosphere. You have the diagonal lanes that are thought to be produced by propagation through density variations within the Io plasma torus, which is a large ring of plasma around Jupiter, consisting mostly of ionized volcanic gases from the moon Io. And so here's an example of these Jovian L bursts. So here you can see these vertical lanes, and then there you can see that diagonal striping. And so you can see this starts at 0618 UT and goes almost 8 minutes later up to 26 UT. So this is a fairly extended 8 minutes period of time. And so this is produced using that dual polarization spectrograph. Another type of observation they're interested in are the Jovian S, or short bursts. And these, by contrast, have a more sharply defined spectral structure. And they typically appear for intervals of a few seconds with a repetition rate to 200 to 400 per second, most commonly around 20 per second. And the individual bursts typically have negative frequency drift on the order of 20 megahertz per second. But because of the high repetition rate and well-defined spectral structure, a high temporal cadence is a requirement for S-burst observation. And so the dual polarization spectrograph is just too slow to sufficiently resolve this. And so what they came up with was another instrument, which they call the Tunable Wideband Receiver, or TWB. And this is an SDR instrument built around a I believe, an oscilloscope card. It has a 2 megahertz bandwidth, and it's capable of resolving spectrum at 205 microsecond cadence for 250 milliseconds at a time. And although it has limited bandwidth and duration, the spectral structure of the S bursts can now be well resolved. And so here's the dual polarization spectrograph, 2-minute duration. And so you can see the S bursts all through here. If you look at this white box, you can zoom in and you can see this, but you can't actually resolve the spectrum with the DPS. But if you go to that TWB instrument, you zoom in here, you can now see over a 250 millisecond period, you can really resolve these beautiful signatures. So all of this is very good, but if the TangerineSDR should be able to also make these same types of measurements and do it in a significantly smaller device, but also more importantly, have a big performance increase. Because a major advantage of a software-defined radio instrument over a swept frequency instrument is the SDR has 100% integration time, because the discrete Fourier transform effectively samples every frequency channel simultaneously. And so if you compare it to an equivalent swept frequency instrument like the DPS, an SDR having the same type of characteristics, you could expect around a 10 dB greater signal to noise ratio. And that would give a much cleaner picture of the Jovian decametric emissions shown here. And so here are the some selected key specifications of the TangerineSDR, which we are expecting to meet. So again, highly stable clock, parts in 10 to the negative 10th for 1 second averaging, and parts in 10 to the negative 12th for 1,000 second averaging. And that's using the GNSS disciplined oscillator with the TCXO. We expect to have plus or minus 50 nanosecond time stamping accuracy, and that time stamping will actually be done in the FPGA, whereas a lot of other systems, if you get your commercial low-cost communications SDR, you'd have to do the time stamping on the computer after the sample has left the FPGA, gone over the Ethernet or over the USB, and then you have to timestamp in the computer. So we'll be timestamping right in the FPGA as early as possible. We'll have phase lock measurements from multiple antennas. So a single TangerineSDR will be able to have up to 4 phase locked RF inputs per data engine by using two RF modules, each with 2 inputs. And what's nice is the clock module has a clock signal input output, where you can synchronize multiple data engines. So you can actually chain all of these together, so you can have as many phase lock measurements as you need. We have the facility for processing and transporting the wideband data. So right now we're using that Intel Max 10 FPGA and gigabit Ethernet. This will give us up to 20 to 30 megahertz of spectrum data that can be sent over the line to a computer to be processed. You can also do some processing directly on the FPGA. And then the measured signal and noise calibrated amplitude will have the onboard switchable noise source with a switching time of less than 15 milliseconds, and the fixed excess noise ratio close to 15 dB. And we will have that open software and hardware architecture. All the software is being released via GPL version 3, and the hardware via hardware Tapper open hardware license. And so a little bit more on that. So ultimately, as I said, the PSWS is being designed to create a network of stations working together under the central control for space weather observations. But the system is open and allows the owner to take full control of their local node if desired. So if you want to just get a TangerineSDR and you don't want to participate in the personal space weather station network, that's totally fine. You can adapt it for use with your radio astronomy application. So even with the standard software that will come with the TangerineSDR, the plan is to provide raw or minimally processed wideband IQ streams over the gigabit Ethernet. So you could process this on your computer however you want. You can also go in and if you feel comfortable with it, you can modify or rewrite the FPGA code to do whatever customized data processing you want right on the FPGA, possibly reduce the data down there. And this approach allows the system to be used for radio astronomy and other applications. So immediately with the current design, it will be usable for radio astronomy applications in the range of 0.1 to 60 megahertz, or yes, 55 megahertz with the that low pass filter that's in there. The system can also be used in other frequencies with appropriate front end filters, low noise amplifier, and a down converter, or you can run it in an undersampling mode with a appropriate filter. If you do that, you might be able to use it for other potential radio astronomy use cases such as pulsar detection, the VHF through microwave bands, or the study of galactic neutral hydrogen clouds using Doppler shift around 1.42 gigahertz, or the study of the age of reionization neutral hydrogen observations around 70 megahertz. So again, if you do something to down convert the signal. So future work beyond the scope of the personal space weather station, TAPR does intend to create additional versions of the TangerineSDR modules, including a data engine with a larger FPGA and 10 gigabit Ethernet, which would allow for a wider bandwidth data, and RF modules with different frequency ranges and transmit capabilities. So where are we right now? The design of the TangerineSDR is complete, and we have almost all the parts to actually build prototypes, initial build of 25 units. But we're running into a bit of trouble right now because of this global chip shortage. So that FPGA we've designed around is currently not available, and they say we'll hopefully get it by February 2022, which is unfortunate. Hopefully we'll get that. In the meantime, what we do have is we have the FPGA development boards, which has the actual FPGA on it, in a slightly different form factor than what we want to use, but we can develop code right on that development board. And we also can, we're working on building adapter modules that will let us plug the RF module and the clock module right into the FPGA development board. So essentially we'd use that development board as a substitute data engine. And this will allow for the code development and the testing of the RF modules and clock modules. And if all goes well, we'll have fully working prototypes within a year. And so in summary, HamSCI is a collective that aims to bring together the amateur radio and professional space science research communities for mutual benefit. And we are looking to improve the scientific usability of amateur radio observations. So we're designing this personal space weather station with science requirements in mind, which includes HF radio receivers for studying the ionosphere using signals of opportunity, ground magnetometers with about 10 nanotesla resolution, GNSS receivers for precision timestamping and frequency stability, a target price of $300 to $1,000 depending on the capability. And the TangerineSDR specifically will have broad applicability to radio astronomy applications, especially radio Jove. We're hoping to have working prototypes within a year. Of course, I'd like to thank the National Science Foundation for their funding, the Amateur Radio Digital Communications, ARDC, for their funding, all the many volunteers who've contributed to the engineering, testing, design, and data collection for this, and the RBN WhisperNet PSK Reporter, all the open source software we use, and the FARLAP Ray Tracing Toolbox by Manny Cervera. So thank you very much. I'll be happy to take questions.
Well, excellent, Nathaniel. I've got questions and comments from Monroe, Ethan, and Les. Let's start with Monroe first. Why don't you go ahead and just ask your questions?
Sure. I see a lot of creation of new and better SDR devices, and I don't know that everyone sees everything that's going on out there in parallel to their efforts. So everyone wants to, invent from scratch. And I've been looking at the equipment market as used by the 5G cell towers and diagnostic equipment. It came across this thing. It was initially a crowdfunded thing by a group called Fairwaves. And their product name was XTRX. So it supports transmit as well as receive. But they got enough attention to get over $700,000 in funding to do this. And then they kind of went radio silent. My suspicion is one of the big 5G equipment vendors kind of sucked them up. But what they produced was an SDR that was embeddable, so you could put multiple of these in a single system. And instead of using Ethernet or USB, they actually went for the maximum bandwidth and went with PCIe, and you can have an X1 or an X2 at the gigabit per second level of data communication. Now, it's only 12-bit because when you start doing your ADC samples at gigabit levels, you can't go really wide on it. But I provided a link in the chat window to take a look at that. The second question I had was the time stamping, and I've tried to do a little bit of this sort of work with the software array that I'm trying to work on for amateurs, definitely at the low end. We call it dirt cheap. But the amount of data bandwidth that you have over these interfaces is somewhat limited if you want to sample at higher rates. And we found that you can't put a timestamp in its fully populated form on blocks of samples. It just consumes too much of the resources, too much of the bandwidth, too much of the storage. So we considered the concept of a baseline fully populated accurate timestamp and then relative offsets for each sample. So, you know, it would allow you to reduce the amount of data being transmitted and stored.
Mm-hmm. I think we will be doing something probably similar to that. I don't think every single sample is going to have a timestamp on it, but what we will be able to do is basically guarantee either stamp every second and then guarantee that the proper number of samples come out in between, so you don't have so that you can deterministically figure out what the timestamp is on each sample.
Okay.
So basically guarantee that nothing gets dropped or the correct number come out.
Yeah, that's often a problem when you're trying to run at maximum speed over USB.
Yeah, and we're not
and dropping.
Yeah, and so that's why I know we have USB 3 on there, but we're actually probably dropping USB 3, and we're really going to focus primarily on the Ethernet rather than the USB because of the latency problems and the dropping problems with USB.
Okay.
Yeah, we've had that problem too. Ethan, you got any questions? Ethan Waldo? Oh, go ahead.
I see the one about how will the undersample work with that fixed low pass filter prior to the ADC. I guess that would not work. So I would think for that case we'd probably have to remove that low pass filter.
Okay.
But certainly the down converting technique would work.
Okay, Les. I think that was your question. You got any other questions? Oh, you're on mute. There you go.
Can't expect me to remember everything. It goes back to the previous question of the how you're going to associate the metadata with the samples. What protocol do you plan to use?
We're planning on using the protocol defined by the MIT Haystack Observatory, which is called Digital RF. So MIT Haystack Observatory uses this with their large incoherent scatter radar system and other experiments. So we'll be incorporating that. I think exactly at what level that stream gets put together, I don't think that has been fully developed yet, but because we're still writing that FPGA code, I'd have to, I could get back to you though. I think Bill Engelke would be able to get a good answer for that, but we'll be using digital RF.
And I assume you know what Beta 49 means?
Yes, I know that's that MITRE standard that software-defined radios use for sending out IQ data over the line.
Exactly what you're doing.
Yeah. So I think we'll make sure we've talked about making sure that's compatible with that.
You.
Great. And we had another big debate on the morning session yesterday about Meteor detecting meteors and the how to detect Doppler using you know, these kind of systems. And the question was, you know, can you detect a meteor from the meteor trail? Can you, using figure out the Doppler, can you detect the direction the meteor came from? Any thoughts? Or is that
I'm not sure. I haven't looked at that problem. I would guess that maybe you could, if you have a distributed network of these receivers and you're able to measure the Doppler from multiple different locations, you might be able to work that out, but I haven't thought that through.
Now you can detect the Doppler on the upper winds and things like that, or the upper ionospheric layer. And
yeah, I know Superdarn can detect Doppler, and they can get meteor winds from that. I believe ISRs have a meteor mode as well, so there are techniques for doing that.
Okay. Just realized you got a bunch of meteor guys in this group who probably use the same technology for meteor detection.
Right. That makes sense. All right, and they're usually doing that around what, 50 megahertz or higher?
Yeah, they're trying to get a good bounce, some kind of good transmitter to use, since the analog TV stations went away. So a lot of people are looking for that, and they just had look at the presentations. They were using WWV for one of those. So you might look at some of the proceedings and see if you can incorporate the same thing to a meteor, and then you have another group to jump on your community.
That sounds great.
All right. Anybody else have any questions to Nathaniel? All right. Excellent, Nathaniel. And by the way, everybody should check in on the HamSCI website. I think there's a lot of good stuff that you all use for as ham radio and radio astronomers. And they have it. When's your next HamSCI convention? And
our plan is having it March 18th through 19th at the University of Scranton. So I'm working on planning it now.
Are you accepting any papers yet?
No, we don't have a call for papers open. I mean, people are welcome to email me, but I'm sure we'll probably have that call in the fall through early like January or so.
Okay. All right.
I can tell you we do have our invited speakers already lined up, and we are putting the finishing touches on the plan to submit for the grant for the workshop. And if everything goes right, it should be really good.
Excellent. Excellent.
Thank you.
All right. Thank you very much. And